Hello, now we will talk about Chapter 7, Section 3, which deals with sampling distributions for means. And so first of all, let's, to explain the concepts of this section, I think it's probably best to just talk about it in a context, in other words, within a problem. So the first context says this: it is thought that the times that it takes workers at a clock factory to assemble clocks have a mean of 22.4 and a standard deviation of 3.2. The manager at the factory takes an SRS of 40 of the workers and finds that they assemble clocks with a mean of 23.1. Assume that the true mean is actually 22.4. Now, first of all, you'll notice nowhere up here does it say it varies approximately normally. When we've had problems like this in the past, it'll say, hey, it varies approximately normally, or possibly it'll vary uniformly, but we don't have that here. And so we'll talk about how it's going to vary in a second, but let's identify these numbers. First of all, it says the true mean, in other words, for all of the workers is 22.4. So that's our mu. That is our population mean, our mean for everybody. And it also says, by the way, that the mean time that it takes all the workers, the mean is that, but it says the standard deviation for all the workers is 3.2. So that is a sigma. That is a population parameter. There's our population standard deviation. It's not our sample value. Our sample value, there's our sample size of 40. That's our N, okay, of the workers, and finds that they assemble the clocks with a mean of 23.1. So that is our sample mean. That is our X bar. That is our estimate for that. So, so that's that. So let me, to describe a sampling distribution, let me just say this to you. First of all, let's talk about what a population distribution is. A population distribution is every value in the population. And in this case, it is the times that it takes the workers to assemble a clock. So they are going to be centered around 22.4. That's the mean, the average. And that's all these X values, not X bar, but X. Every one of these is a single worker's time. So the population distribution is every value for every worker. And you would assume that there's hundreds of workers here because our population size needs to be at least 10 times our sample size. So it needs to be at least 400. So the population is every worker's values. So that is all. Let's just pretend there's 500 total workers at this factory. So there would be 500 X's. So that's the population distribution. The sample distribution is all the numbers in the sample. So in this case, it's 40. So it'd be the 40 values, all right, that are from the sample. And they are centered around 23.1. So there's the average of the sample values, and there'd be 40 of these X's, 40 of these numbers in essence in the sample. What the sampling distribution is, it is every value the sample statistic can take. So for one statistic, all right, they take 40 values and they average those 40 values, and that gets me an X bar, okay? Now, the sampling distribution, as long as you've done it in an unbiased way, which we've taken a simple random sample, so it's an unbiased, but they're going to be centered at the true mean of 22.4. So this is like, so this would be like 22.4, and our sample value was 23.1. That is what we got in our sample, okay? The concept of a sampling distribution is, what if we did this again? What if we get another sample of size 40 and found another mean? It's going to vary from this first mean just because of sampling variability. And if we kept getting many samples of size 40 and found many means, finding the mean of the 40 values, this sampling distribution, this collection of sample statistics is what we call a sampling distribution. It is every value the sample mean can take. So now to describe the sampling distribution, to describe these values, we have to, just like earlier in the year when we described distribution, we have to cuss. In other words, describe their center, their unusual values, their shape, and their spread. So let's start with the center, okay? And I don't have a copy of the formula sheet handy, but this is on your formula sheet. So actually, I'm sorry, I believe I do. Let me show you where that is on your formula sheet. And so on your formula sheet, it's on the second page of your formula sheet right here where it says sampling distributions for means. So for one population, which what we're dealing with here, is that the mean of the X bars is equal to mu. So the mean of these X bars will be like this. It will be equal to mu. So mu of X bar is equal to mu, and that is equal to 22.4 minutes. So that would describe the center. Now let's talk about the spread. So the spread in this case is described by the standard deviation. Well, go into our formula sheet again. The standard deviation of these X bars is equal to sigma over the square root of n. We could prove that little formula, but we're not going to take the time to do it here. And so the standard deviation of the X bars is equal to sigma over the square root of n. And so that is equal to 3.2 over the square root of 40, like that. And you could just leave that like that. That's equal to approximately 0.50596. And so that takes care of the center and the spread, the shape. How do we know the shape of the X bars? We don't know the shape of the population values. It doesn't tell us. And this is what we call the central limit theorem. The shape is going to be approximately normal because our sample size is large. Approximately normal because our n is greater than or equal to 30. And that's sort of an amazing thing in the world of stats, and it's what we refer to as the central limit theorem. These, as long as our sample size is large and with means bigger than 30 or so, these X bars will be approximately normal because of the central limit theorem. Or if it had told us up here the population varies approximately normally. So anyway, and by saying it's approximate normal, that takes care of the unusual values as well. It describes the nature of the outliers. So that is what we would say. You would say the distribution of X bars, the sampling distribution, has a mean of that, a standard deviation of that, and the shape's approximately normal, and that will take care of that. What is the central limit theorem? Here's what the central limit theorem says. If your sample size is large, if your n is large, and by large, we mean greater than or equal to 30 or so. That kind of differs from book to book, but in the world of AP stats, we've decided upon 30. Okay, the sampling distribution, not the sample distribution, the sampling distribution will be approximately normal. With mean equal to the mean of the X bars equal to mu, and the mean or the standard deviation of the X bars, the sigma of the X bars is equal to sigma over the square root of n. So that is what the central limit theorem tells us. Now the sampling distribution will also be approximately normal if it said up here that the population varies approximately normal. So let's say your sample size was like 20 or 10, something below 30. It would have to say approximately normal up here, or you wouldn't have approximate normality in your sampling distribution. And so that's what the central limit theorem is. So why is the sampling distribution approximately normal in this case? And you would say just because our n is equal to 40, and that is greater than 30. So by the central limit theorem, the sampling distribution, the sampling, please say sampling and not sample, please. Okay, it's not the sample distribution, it's the sampling distribution. Sampling distribution is approximately normal. So that's how we know that in this case. And thus we can use normal CDF or inverse norm or normal functions. What fact allows you to use the formula for the standard deviation? This is also true when we did proportions in 7.2, is that our sample size cannot be more than 10% of our population size. Okay, the sample can't be more than 10% of the population, because when we do sampling without replacement. And every time we take someone out of the population, we're changing the population slightly. But as long as the population is big enough, it won't make a significant difference. And how big does it need to be? Well, it needs to be at least 10 times the sample size. So anyway, so here our sample size is 40. So therefore, in our population size must be at least 400. Okay, for our population size to be at least 10 times our sample size. And so that's sort of our theory. You just need to memorize the normality thing and then memorize that. So those are common questions, and so you need to be able to answer them in that way. And don't get the normality thing mixed up with the thing for proportions. For proportions, you have normality if n times p and n times 1 minus p are greater than 10. Okay. For means, if your sample size is bigger than 30, or if it says the population varies approximately normally. So in this case, it says if it really does take the workers an average of 22.4 minutes to assemble a clock, what's the probability you get a sample mean of 23.1 minutes or more in a sample size of 40? So now we have normality in our sampling distribution. Here's all our possible values of X bar. So they are centered at 22.4. And so our sample mean is 23.1, which is somewhere above it. I mean, one standard deviation above it is like 0.5 more. So this would be like 22.9 something is one standard deviation above it. And so 23.1 is somewhere up here. I'm just drawing this to orient myself to find my area. And so the answer to this question is this area that is above 23.1. That represents the probability of getting a sample value, probability of getting an X bar greater than 23.1. And so this is a normal curve. And once again, why is it normal? Because our sample size is bigger than 30. And so we can use normal CDF. So I'm going to write normal CDF from 23.1 to infinity. Our mean is 22.4, and our standard deviation is going to be 3.2 divided by the square root of 40. Label this as lower bound, upper bound, mu of my X bars, sigma of my X bars, like that. And that would be properly showing your work. Just right, please label it like that, just like we've been doing since chapter 2. So let's use our little calculator. So once again, normal CDF, we'll go to the distribution menu right above the VARs button. And so we go second VARs and go to normal CDF. And so we are going from 23.1 to infinity, or just put a big number like 9 billion or something. And so then 22.4 and then 3.2 divided by the square root of 40, like that. There we go. And so then we click that and that. And so that gives me 0.083256, okay, which there you go. That is what later in the year we're going to call a p-value. Okay, or a probability, the probability that assuming 22.4 is true, that we would get a sample value this bigger. So it's greater than 0.05, so it's not statistically significant. Okay, in other words, we wouldn't be surprised for that to happen at all. Okay, number 5, how large must your sample, how large would you have to make your sample size if you wanted the standard deviation of the sampling distribution to be at most 0.25? Well, once again, our formula for the standard deviation of our sampling distribution, the standard deviation of our sampling distribution of our X bars is going to be equal to sigma over the square root of n. So we want this to be at most 0.25. Okay, so this thing, and so we're going like that. We want this to be either 0.25 or less than that. And so our sigma is 3.2 over the square root of n. And so we just have to solve this for the square root of n. So I'll just use my algebra skills to multiply both sides by the square root of n to get it out of the denominator. And so I'd have the square root of n times 0.25 is greater than or equal to 3.2, and then just divide by 0.25, divide by 0.25, and let's see what we get. And so we would get that the square root of n is greater than or equal to, and so that will be 3.2 divided by 0.25. So that's 12.8. And so then I square both sides. So n is greater than or equal to, and so I'll just square that. And so I get 163.84, 163.84. And so I just round that up. And because a sample size has to be an integer, and by rounding it up to 184, I'm ensuring that the standard deviation of the sampling distribution will actually be a little bit less than 0.25 by rounding it up. And so, and in general, the bigger your sample size is, the smaller your standard deviation or your sampling distribution is. And notice the exact relationship. We'll have problems come up we're going to talk about. It's inversely related by the square root of the sample size. Okay, so if I wanted my if I wanted this to be half as big, I would have to make this 4 times as big. Okay, because it's inversely related by the square root. If I wanted this to be a third as big as it is, I'd have to multiply the sample size by 9. That's more of a concept for later chapters. But anyway, so that's that. So let's look at this situation here. It says the salmon in Nicole's ponds have weights that vary with a very skewed distribution. Okay, very skewed with a mean of 8.4 and a standard deviation of 2.7. So we don't know how it varies. Skewed left, skewed right. We just know it's very skewed. If you randomly select one of Nicole's salmon, what's the probability it weighs more than 9 pounds? Well, we don't know how the population varies. So we cannot do this problem. Okay, we have to know how it varies. And so we would say we cannot do this because we don't know how the population or the weights of the salmon, we don't know how the salmon weights vary. We cannot do it. But, and here it says this, if you randomly select 30 of Nicole's salmon, what's the probability that the mean weight of them is more than 9? Now we can do it. Why can we do it? Because of the central limit theorem. Is that we know when our sample size is bigger than 30, the sampling distribution will be approximately normal. And so now we can use normal CDF on this. And so what we've got here is we have normality. We have a normal curve. And so this is normal because of the central limit theorem. And so what is the mean? What is the middle of this normal curve? And that's going to be the mean of the population, 8.4. And what is the sigma of the sampling distribution of the X bars? And every point in a sampling distribution for a mean, every one of these is an X bar. For a proportion to be a P hat. That was section 7.2. So every one of these is an X bar. The average, the standard deviation of the X bars, the average amount these X bars vary from the middle, it's going to be sigma over the square root of n. So that's 2.7 divided by the square root of 30. Okay. And so now, we want to know the probability of more than 9. Well, 9 is somewhere up here. So more than greater than 9 that'd be our shaded area. So that's 9. So to find that area, we do normal CDF. So normal CDF from 9 to infinity, our mean is 8.4. Our standard deviation is 2.7 divided by the square root of 30. Label that LB for lower bound, UB for upper bound, mu of the X bars, sigma of the X bars. That's once again considered showing your work as we've done all year with normal CDF. And so let's do this. So second distribution, which is second VARS, which is distribution normal CDF from 9 to infinity. Our mean is 8.4. Our standard deviation is 2.7 divided by the square root of 30. And so we would get 0.11177. That happens about 11% of the time. In other words, it wouldn't be surprising for us to happen because this is above 0.05. There's about 11% chance that it would happen. So it wouldn't shock us if we took a sample of 30 of Nicole's salmon and got a mean of 9 or more. Okay, so then we have this, and this is an important thing. What is more likely, taking a sample of 40 of Nicole's salmon, getting a mean greater than 9, or taking a sample of 80 of Nicole's salmon, getting a mean greater than 9? So what happens when you make the sample size bigger, all right? And so the concept here is this. The bigger your sample size is, the less your variability is in your sampling distribution, and the more unlikely you're going to get values that are a certain distance from the mean. So first of all, let's just find these values using normal CDF. I had a problem like this on the AP exam one year, but it didn't give you the mean, and so you couldn't figure out the value, or it didn't give you the standard deviation rather, and you just had to understand the concept of the bigger the sample size is, the less your variability is. So let's find it with 40. So we would say normal CDF. So the sample size is 40 greater than 9, so it'd be 9 to infinity, and the mean is still the same, 8.4, and then this would be 2.7 divided by the square root of 40, lower bound, upper bound, mu, sigma. Okay, so let's see what we get. And so I'll just go ahead and change this to 40. like that. And so we would get 0.07994. So that would be 0.07994. Okay. But now if we change it to 80, it would be all this is the same, but now this is 2.7 divided by the square root of 80. Let's see what happens. So if we change this to 80, now that is 0.023427. So that is statistically significant. In other words, it's less likely to occur. So the one with 40 is more likely to occur. And so how do you explain that? Which is more likely, taking a sample and getting mean greater than 9 or taking a sample of 80? And the answer would be A, the sample of 40 is more likely. There's about an 8% chance, only a 2% chance with a sample size 80 is more likely because the smaller sample size creates more variability in the sampling distribution. So values a certain distance from the mean, or greater are more likely. And we always do activities in class that sort of demonstrate this. But what's going on here is this: the sampling distribution, all the possible values of X bar for, let's say our sample size is 40. And so so here's our mean, which in this case is, is 8.4. And so our X bars, if we were to graph them, let's say they would look something like this. Let's say you'd definitely be normal because this is certainly bigger than 30. But with a sample of size 80 is what's going to happen is, all right, it's going to be skinnier. It's there. Things get more condensed around 8.4. Okay, here's a sample size 80. It's going to go like this. It's going to go whoop, like that. It's going to be really taller. And so it's going to be taller in the middle. And then the tails are shorter here. And so if you take this, like, let's say 9 is here. Let's say 9 is there. It's really unlikely to happen. Only a few X bars are up here. There's not much area here, but there's a lot more area here. So values away from the mean a certain distance, in this case, like 0.5, a distance of 0.6, okay? They are much more likely to occur with a smaller sample size because there's more variability in the sample distribution. There's an inverse relationship between sample size and variability. Okay. As a matter of fact, it's inversely related by the square root of the sample size. Okay, that's it. Now that is the first part of 7.3. The second part of 7.3, we're going to talk about 2 sample things, but that's the main thing in sample 3. So thanks for watching, and then there will also be a part 2 of 7.3 that will be posted as well. So thanks for watching.